Thank you. So it's really a pleasure to be here, and I was really worried about giving this talk, but I'm much more comfortable after hearing Jonathan's talk. And for one reason is I'm actually just going to pick up on a little point that he made. He called it visualization is not explanation. I'm going to tell you sort of my take on that. I also found out he's into Python, and I'm actually going to show you some Python. So if you like Python, I'll get to show you that. But most importantly, actually, he made me realize something that I never realized. And my job is not that different than a lot of your jobs. I'm talking to the journalists. I'm a teacher. And as a teacher, my job is to explain things to people. So all day, pretty much, I go to class and I explain things to people. And I think the main difference from what I can tell is sort of my audience and what I'm trying to accomplish. I mean, my audience, I teach at Stanford, so I have these incredibly bright students, and mostly what I do is try to teach them how to think. That's sort of my philosophy. I'm not teaching them specific facts, I'm trying to teach them how to think. And the way I do that is by taking really basic ideas, like what I consider fundamental ideas, and making them easy to understand. And what I want is them to understand them deeply. I want them to really comprehend a simple idea, and I'm going to give them this little tool that they can apply in their life. So that's actually what I'm going to talk about. I'm going to actually, what I decided to do is just show you an example of something I developed in my visualization class, actually. And I'll get back to this, but really the point of my talk I'll come back to is you can't just show them things, you have to explain them to it. Explain them. So, is this working? Okay. Good. Is that working now? No. Okay. Anyway, so we've all been really interested in data. So let me just start it out by I want to talk about something related to data, which are algorithms. And I actually think, as a computer scientist, the algorithms are actually the more interesting part to me than the data itself, because the algorithms are what we do with the data. It's how we process the data. Since I'm in computing, it's all about how we process the data. And I've been talking to some people that are interested in explaining algorithms behind data. In fact, I have a friend who's trying to make some something for NPR about algorithms. Of course, algorithms are really a hot subject, right? Because how does Google rank pages, or how does Netflix recommend movies, or how does eHarmony match you up with somebody, right? These algorithms are running, or how does Watson win at Jeopardy? These algorithms are what's getting lost. People are talking about the data, but not talking about what people do with the data. So I'm trying to explain to people why algorithms are so important. So I'm just going to tell you a little explanation I gave on Euclid's algorithm. And I picked Euclid's algorithm because it's the first, sometimes they'll say it's the first known algorithm. And of course, it's a very simple algorithm. So I just want to explain this algorithm to you. So it's a simple thing, and there's some math in here, but I hope everybody can get this. There's this idea called the greatest common divisor. So suppose we have two numbers, 12 and 42. Each of those have a bunch of numbers that divide them, right? 2 divides into 12. 2 times 6 is 12. 3, 4, 6 divide into 12. 2, 3, 6, and 7 divide into 42. And the greatest common divisor is 6, because it's a divisor of both numbers, and it's the largest one. So that's a really pretty simple concept. Now, what I just actually wrote down is how probably a human would solve that problem. You would write down all the divisors, and you'd look for the greatest common one. Seems like a pretty simple way. It turns out in algorithms that figuring out the divisors of a number is incredibly hard and intractable as an algorithm. In fact, all of cryptography is based on the single principle that you cannot factor a number into its divisors. That's how all cryptographic codes work. So this simple process that we would normally do doesn't actually work. So I'm not going to go into that, but you can't actually do that. That's not a useful algorithm. So Euclid actually came up with an algorithm for computing the greatest one, and you might think that's harder than computing all the divisors, but it turns out he came up with this really simple algorithm for doing this. And Jonathan showed you Python. I'm going to show this too. And I was a little worried about this, but I don't know if did anybody see that Google chat session with President Obama last week, where he said everybody in the United States should learn to code? And there's this video going around, viral video, code.org put it out with Zuckerberg and Bill Gates and everybody saying you should learn to code. Like, there's one thing you want to learn these days is to code. Go watch that video. It's really cool, inspiring. And one of the points they make in the video is coding is really easy. It's a lot easier than making graphics, or it's a lot easier than writing. So anyways, this is the whole program, the whole algorithm for Euclid's algorithm. There's this function, GCD. I'm just going to run it because so in Python, you can just run that. Well, here it is. That's it. Come back to it, and if I just run it, if I give it two numbers, 15 and 6, 15 and 6. That should be 3, right? 3, it did it. Okay, so that's sort of mysterious. So I want to visualize that algorithm. Okay, first step in visualization, print A, comma, B. I run it again. What? Oh, I did that in the wrong place. So I printed it. So I ran that program, I printed it, but I want to print it out as it runs. So I print it there, and now it prints out all the intermediate steps. So one of the tricky things about an algorithm is there's this process involved, right? It's this thing that's running, and it's very hard to visualize these things. So one thing I just did that's really relatively easy to do, it's something called algorithm animation, algorithm visualization. So you just sort of like trace what happens. You just sort of tell it what happens. So all right, and that might be informative to you. But anyways, I was always thinking about how to explain this algorithm, and I went to the Wikipedia page. Wikipedia always has, and it's always a pretty good first source of information. And I'm looking through here, and down here, there's this visualization of it. Now, this visualization, the two sides of this rectangle are A and B, and those are those two numbers, 15 and 16. And so the big one is 15, the little one is 16. And what this algorithm is sort of showing is you're sort of subtracting squares from other squares until nothing is left. So you start subtracting squares until you can't do it anymore, then you subtract some more. And that's actually how the algorithm works. Now this particular principle for visualization, which is to sort of use part the whole relationship, goes all the way back to the Chinese. That's how they proved the Pythagorean theorem, if you've ever seen those visualizations. Okay, so let's go back to this. Now, the first time I was teaching this, I was teaching it in a course on visualization because I wanted to teach about algorithm visualization. And one of the things, of course, you realize is that it's sometimes sort of hard to do animation. Now, this is, I could have a whole talk just on this, but one of my colleagues at Stanford is Barbara Tversky. She has studied how hard it is for people to understand things because of animation. And one of the biggest problems is just motion is fleeting and transient, right? You can't remember what happened, and so on. And I'm not going to spend much time on it, but there's a lot of problems with animation. So in this class, what I was just going to say, well, let's just break it down into a sequence of steps. So we're just going to show the sequence of steps of the algorithm. So here I took the example of 15 and 6. And the algorithm is pretty simple. If you look in the loop, anybody can understand coding. It's not complicated. It says if A is greater than B, subtract B from A, else subtract A from B. So you just look at whatever one's smaller, you subtract it from the other one. And you keep doing that until nothing's left, until B equals 0. Okay? So in this visualization that these guys came up with, okay, we start out with this. The smaller number is 6, and so we're going to subtract 6 from 15 and get 9. Now, the visualization trick is, if I flip this on its side, if I flip the 6 over there, I get a square, and I subtract this from here. I've removed this square, the blue square, from the green square, and so the remaining height of the green square is what's left, 9, right? And now A is still bigger than B, so we do it again. So here's what's happening. Now A is 3, so A is less than B. So you can't keep subtracting B from A because there's not enough stuff left. So you switch to the other way. You take B, you take what's left there, which is the little bit of A, because A is less than B, and you now subtract that from B, right? So you subtracted what was left, A, from B, and then you do it one more time, and you get 0, and the algorithm prints out 3, and that's the greatest common divisor. So that's an algorithm. That's it runs. So I was pretty proud of that, and I was teaching this class. And I was showing them, I said, I'd teach them about animation, showing them. And then that night, I'm sitting there and just saying, what did I do? I showed them the algorithm, but I didn't explain why it worked. I mean, it's very mysterious. I mean, why is that the greatest common? I mean, that just doesn't immediately jump out to everybody. Nobody asked me that, by the way. They were so enchanted with the visualization, they finally understood how the algorithm ran, they didn't ask me how it worked. And so that night, I spent the whole night trying to figure out why this algorithm works, because I realized I didn't even know why it worked, okay? And so now I'm going to explain it to you. And it's really a little tricky, but I want to make it sort of obvious. So here's and this is the visual proof of the math behind it. So we have, say we got the answer. So remember, the answer is that the little orange square up at the top. So we'll call that R, the answer. Just say that's R. The size, that's the length of one of those sides. And so that's okay. That's just the fact. But we would say mathematically that it's clear that R divides B. So B was the horizontal size. And why does R divide B? Everybody get that, right? Because what we did is we subtracted R away from B multiple times until we got 0, right? We did some number of steps. We don't know how many it was. In this case, it was 2. But we kept subtracting 2, and eventually we got 0. Therefore, there was some n times B, n times R was equal to B. So it's clear that B has R as a divisor. Does that make sense, everybody? That's a sort of part of the explanation. And now let's consider B. So now I've just made that thing have a length B, 1 square of length B. And now I'm just going to flip it on its side. And that now has height B. So now, if I subtract that from what was left, the original blue, and I do it again, okay, I get back to sort of where I started. And if you think of it, I just proved that R also divides A. And if you think of it, R, there's, R equals 5 times A, right? There's one piece up there, and then 2 times 2. Okay, that's pretty easy to understand. And so R divides A and B. Hence, R is a divisor, but we just don't know it's the greatest common divisor. Right? It's not necessarily the greatest one. It's a divisor, it divides it, but we have to be precise. We don't know it's the greatest one. There could be another version that did it. So in math, you have to be sort of precise. So we say it's less than or equal to the greatest common divisor. So we haven't proved it yet, but we explained one part of it. Okay, so here's the rest of the proof. So what you do, this is like mathematical reasoning. You say, suppose there is something that divides A. So there's this other thing called D that divides A. I just picked some size. By meaning it divides it, just means it breaks it up into n pieces. And then suppose B also divides A. So in this case, same D. So it has to divide A and B, right? So it divides both of them, right? The exact number. No, this is sort of an interesting thing about visualization. I'm trying to make very general statements in the math, and every time I give you an example, it has to be a specific example. So it's a sort of a tricky thing. And when you're using visualizations, they're always specific. I could have made a different D, like, this could have been twice as long or something. This would have been a different visualization, but sort of the same statement. So the statements are more general. That's why math is still important. You can't just use visualization for everything. But anyways, if we go back to our little diagram that we animated, it's clear that R must be a divisor of D. D must be a divisor of R, right? Because if I took these 4 guys here and flipped them on its side and subtracted it, I would always subtract some integral numbers of these guys. And what's left in the green square will always have to be a couple squares. I can't look at half a square, right? Because the length, this is 4 here, and if I start subtracting 4 from A multiple times, I get 2 left. Because no matter what I do, there always has to be a square there. Has to be some number of squares there. And since the height of that thing is R, then D must divide R. And therefore, any divisor of D of A and B must divide R. And this must work for all divisors. So now we say the greatest common divisor has to be less than or equal to R. Right? Because this is true for all the divisors, so it has to be true for the greatest common divisor. The greatest common divisor is just one of the divisors. I proved that any divisor does it, therefore this is true. And again, we have to be very precise. It's less than or equal, it's not equal. But then here's where you learn math, right? And you say, well, we just showed 2 things. R is less than or equal to the greatest common divisor. We also showed the greatest common divisor is less than or equal to R, therefore R equals the greatest common divisor. That's cool math reasoning. That's what we try to teach people. So, this is just an example, but I tried, this is a couple of things I tried to do. It takes something as basic as the first algorithm ever invented and try to make it self-evident that it is true and to illustrate how we do the reasoning. That's my job. I just give this example, but that's sort of what I do for a living. And I'm not as good, this isn't as fancy of a graphic, but I'm trying to get this deep understanding of the material. I hope you all get this. I know a lot of people maybe don't use math every day, but this is surprisingly sophisticated math that I'm showing you. So, but this example also shows something I've learned, right? Is you start with algorithm animation and with computers, and you record a bunch of information. You collect a bunch of data. So in the case of the algorithm, I printed out A and B. I just printed out everything that happens. That's sort of what sensors do. That's what click streams are. That's what computers do. They just record a bunch of data. And I can show you that data. Like I can show you the animation of the algorithm working and the various values of A and B as it progresses. But that's not that interesting. I mean, it's the first step. And this is why I liked what Jonathan was saying. The real value in visualization and processing data is explaining what it means or telling a story with it. And the problem we're getting into is the first part is getting really, really easy. It's really easy to record data. That's why we have so much of it. It's really hard to explain it. It's really, really hard to explain. So as a technologist, this is one reason Tableau is really interested in this conference, is we think this is the big challenge, is how to explain it or reason about the data, not just how to show it. And we want to sort of move on beyond just showing it. And so that's why I picked this title, Showing is Not Explaining. And actually, I have to say, I didn't actually invent this phrase. I have a colleague, a psychologist at Stanford, Barbara Tversky, who actually explained this to me for the first time. So thank you very much.